The subject, well, this reminds me that today we've been talking a lot about the electrical utilities, but so much of this also applies to, water, sewer, communications, gas. Um, but talking about the grid, I mentioned in the intro about everybody says we got to update the grid. The grid resilience is a real key focus globally and here in the United States with this recent bill that people have been talking about. So here to discuss this, go into this a bit further is Brian Flett. He's a senior director of product management with Bentley Systems, one of our sponsors. And Brian, look forward to hearing from you. Take the floor, sir.
All right. Well, thank you very much. As Gavin said, my name is Brian Flett. I'm with Bentley Systems. We build software for designing and building and running the world's infrastructure. And I'm responsible for our energy portfolio solutions. And I thought I'd talk today a little bit about how we've been working with some electric utilities to apply this digital twin technology to improve grid resilience. And I thought I'd start off with an example. This is a rudimentary example, but it gives you an idea of the kinds of things that people are doing with digital twins today. This is and we try and start with a business problem to solve or a challenge to solve. So in this case, we're talking about an organization that had a number of substations. The substations were designed and built years and years ago. Lots of equipment has been sort of added and removed from those substations over time. And now they're seeing more severe weather events, and they're concerned about lightning. And so they want to take a look at the model of the substation and specifically whether they've got adequate lightning protection in that substation. So here, they've created a pretty rudimentary model of the substation by just flying some drones and creating a mesh of the substation. It doesn't have details about the equipment or any of that kind of information, but it is enough of a model for this particular use case, which is to determine whether the tops of the lightning rods are going to provide adequate protection to the equipment that's in the substation. So by pulling this model into an engineering design tool, the design tools have capabilities for doing things like lightning analysis, where you click on the top of your lightning rods. It will show you, it will sort of create this virtual tent showing you if equipment is underneath the tent, it's protected by the lightning rods. If it's poking through the tent, then it's at risk, and you may want to consider adding other lightning rods to the site to make sure that you fully protect all of your equipment in the environment. So that's just one sort of example, but I wanted to walk through some of the variety of challenges that we're seeing in utilities. Barbara was starting to talk about that. Barbara and Craig were talking about some of those challenges. I want to dig into that a little bit further for some of the challenges that we're seeing in our electric grids, and especially the resilience of our electric grids. Talk a little bit about the different types of digital twins that you can build to address those challenges. And then go into a few other examples of use cases of applying those digital twins to maybe more sophisticated problems where a more sophisticated digital twin might be required. And then talk a little bit about the steps to building the twin, some of the important concepts for the twin itself, and how to get started. And certainly, please, as I'm going through this, please do add questions to the chat. I think that's often the most interesting part of these presentations is the Q&A at the end. So, challenge. What sort of challenges are we seeing? As Craig pointed out, most of our grid, most of our network was built, 50 to 100 years ago, and there are lots of existing challenges to that grid. From wildfires, which are becoming more and more prevalent, especially in the West Coast, vegetation encroachment, aging infrastructure, all of those are sort of traditional challenges that we've seen in our transmission and distribution grid. But we've got internal challenges in our organizations as well. We have a vast variety of information, lots of different information sources. Our problems are often not lack of data, but lack of ability to access and understand the data coming out from all of those systems. So we see one of the advantages of a digital twin is to be able to provide sort of a line of sight across all of your existing systems, to pull data from that, really understand what's going on out there, and then use that to address some of these challenges. And these challenges have been with us for quite some time, but there's a bunch of new challenges coming with the drive to renewable energy. So certainly the energy transition is having a couple of impacts on our grid. One is it's increasing demand because more and more things are being electrified. But the other thing it's putting generation in the middle of our distribution network. I mean, it used to be that you generate centrally, you shoved your electrons down the transmission wires, and it got consumed in your distribution grid. Now we've got windmills on farmers' fields, we've got solar panels on people's roofs, we've got households that are consuming electricity when it's nighttime, but actually providing electricity during the day. And a lot of our equipment wasn't really designed with this two-way power flow expectation. And so there's a lot of new challenges coming with these distributed energy resources. And again, we think one of the keys to challenging or to meeting those challenges is to be able to have a digital representation, a digital understanding of the network, of the engineering, of the constraints on which it was designed from an engineering perspective to begin with, its current condition, and then use that to assess if somebody's thinking of putting a new solar panel on their roof, or if somebody's thinking of putting a new EV charging station down the street. Can the network handle that? Do you need to adjust some of your equipment? What do you need to do in order to support these sorts of use cases? So those are kind of some of the types of problems that we see being able to solve with a digital twin. And when we think of a digital twin, we think there's a number of different sort of levels of granularity and levels of sophistication for that twin. So certainly, here's our substation again. We had, our first substation example was a pretty rudimentary digital twin. If you can think of a more sophisticated digital twin, you could have, for every piece of equipment in the substation, that equipment vendor might have created a digital twin of that piece of equipment that helps you understand the various ways it can fail. If there's likely sensors that came with that piece of equipment, the vendor may be able to provide information that tells you how to monitor what's coming from those sensors over time, and then use that to assess the health of that particular piece of equipment. And if you understand the connectivity of all your pieces of equipment in the substation, and the protection and controls that you designed into the substation when you built the substation, that gives you sort of the second level of sophistication. Now you want to have not only a digital twin of the individual equipment, but you've got a digital twin of the substation itself. And same sort of idea. If you can understand the health of the equipment and what's going on, then you can assess what's going on in that substation. And so we think, one of the key advantages of the digital twin, because it's three-dimensional, because people can understand it and look at it and sort of intuit what's going on out there, it provides much better access to data. So if we can tie in all of these legacy sources of information that are sort of dark data perhaps today, and provide people access to it through this visual and intuitive interface, then people can gather intelligence, gather much better insights from that data, and actually trigger action from the data. And of course, it's not just about individual substations, but it's about the world as a whole. And certainly in a utility, you have a variety of different generating assets, transmission assets, distribution networks, and things like that. And so having a model of the entire organization or even entire network, which may be composed of multiple different organizations cooperating. Again, having that that kind of model allows you to do what-if analysis and assess different possible ways of reacting to opportunities. So that's sort of our concept of what a digital twin is. We see the digital twin being able to be used by sort of a variety of different personas and a variety of different use cases. And in this, in this short presentation, I'll just dive into the asset manager and the asset management use case, and talk about some of the ways a digital twin can help the asset manager ensure the resilience of the grid. So if you're an asset manager, what are some of the key things that you want to do if you want to ensure a resilient grid? Ideally, the first things you should be doing is taking a risk-based approach. So you want to be taking a look at identifying the risks in your grid. How can things fail, whether it's through asset degradation, whether it's through weather events? What are the various different risks of problems in the grid? What are the consequences of those events? So if a particular transformer fails, do you have redundant capacity? And is that something you can recover from quickly? Or is that a single point of failure and you actually need to repair that thing before you can provide power to your customers? How many downstream customers have you got and who's going to be impacted by this? All of that is sort of part of understanding the risk that's associated with the current configuration of your grid. Then there's sort of a suite of requirements around monitoring the performance of your grid. So understanding the health of your equipment. And again, by tying into multiple legacy systems, you can get a full picture of the health of that system. So you may be tying into SCADA systems, which are telling you about load peaks that have been happening over time. You may be tying into feedback that you're getting from oil analysis labs, if you've done oil analysis over time on these pieces of equipment, and obviously tying into physical changes that you can see through some of the tools like we've seen earlier today. Regulatory compliance is another key area. Utilities need to not only be monitoring the health of their equipment and managing the health of the equipment, they need to be proving that to their regulators, and regulators are getting more and more strict around ensuring that that the utilities can prove that they are managing their grid in a responsible manner, and ultimately, taking a look at your asset portfolio over time. So here's another substation example, but in this case, the substation digital twin that's required, it's a little bit more sophisticated. So here we've got a combination of a three-dimensional CAD view of the substation equipment, juxtaposed on top of a reality mesh of the surrounding vegetation to give us a picture of the complete substation. And we've taken this this three-dimensional CAD model, and which has obviously information about the engineering characteristics of the equipment and things like that. And we've tied it together with protection and control diagrams, so that if you click on an object in the CAD model, you zoom in on the object on the 2D model and vice versa. But we can also tie it in with real-time information and real-time sources as well, to get a full picture of not only how the system was designed, but how the system is currently operating. And since all of this information is digital, we can use algorithms and machine learning where appropriate to trend this information over time. So let's say that we've been collecting oil samples, and we've been collecting load peaks, and we've been collecting visual inspections of all of this equipment, and we've been trending this over time. And we're noticing that this particular piece of equipment is trending towards failure. And the system can calculate all of that. You can have degradation models for each of your pieces of equipment to understand that they're trending towards failure. You can highlight that piece of equipment is something that you need to look at. And then you can immediately drill into, first of all the sources of information that that caused this thing to go into alarm. Was it the gas analysis? Was it the temperature of the oil? What is it that, how does that compare with the OEM recommendations for this particular equipment? All of this can give you a flavor for the health of that equipment. And then ultimately you can decide to act on that. And if you wish, you can trigger a work order directly into your work management system to actually have someone go out and perform some maintenance on this piece of equipment. So the idea here is the digital twins being used to, yes, it's being used to kind of visualize and understand what's out there and the equipment, the health of what's out there. But it's also being used to act on that, and it's ideally integrated with your operational systems, so that so that you can actually trigger events to happen in real time in your operational systems. So that's sort of what we think is are some of the some of the benefits of applying a digital twin approach to this type of problem. You get actionable insights. You have a model that you can kind of intuitively consume. It provides a single view of the truth. The actual source of truth might come from a variety of different systems. You might have a GIS system, which is your source of truth for location, and an asset performance management system, which is your source of truth for condition. But all of that can be pulled together and kind of visualized in a way that that humans can understand and can use to trigger follow-on events. And then over time, you can some of the more rudimentary decisions you can automate, and so it becomes the digital twin becomes not only a tool for humans to understand what's going on out there. Since it's fully digital, it's also a tool that you can have AI and machine learning act on and automate certain decisions. So that's those are a couple of substation examples. Moving out of the substation, and vegetation management is kind of another example. And here, similar to what we've seen before, certainly understanding the changes over time is a key component of the digital twin. So here we're taking a look at a distribution network and some of the vegetation on that distribution network and transmission lines that are going through there. And we can see where vegetation is getting close to that transmission line. And if we're if we're collecting this information on a regular basis and turning this into a model, we can actually trend the growth in vegetation the same way we can trend the degradation of equipment. And then people can easily see that things, even if the vegetation isn't encroaching on the equipment yet, it's liable to in the near future based on how the growth is trending over time. And we can raise issues, send out work orders, whether it's a work order to a vegetation management group to do more inspections or to actually trim the trees or whatever. We can certainly incorporate all of that into this system. So let's talk a little bit about what this digital twin is. From our perspective, it needs to be an open system. It needs to be an open system from a variety of different perspectives. There's no one vendor that you can buy a digital twin from. We don't think. We think a digital twin is an ecosystem of capabilities from a number of different vendors and leveraging a bunch of your existing data sources. So certainly you want to select an environment which is which is open from a couple of perspectives. One is you want to make sure it's open to any design tool, any GIS, any SCADA system or CMS management system. So you want a system that can talk to any of those kinds of data sources. But you also want a system that is open itself. In fact, what we decided to do is open source our platform code and encourage others to build upon it, because we definitely see this as an ecosystem, and we see it as something that we need to collaborate on with other companies in order to come up with a complete solution. Certainly, the digital twin should be able to consume and make it easy for people to visualize historical data over time. This time dimension that Peter mentioned is absolutely critical to this twin, and ideally you can use that historical data to then simulate, either run simulations through the software of future actions, or run AI and ML on that historical data to predict how things are going to trend into the future. So it's about a combination of photogrammetry, it's a combination of LiDAR, it's a combination of CAD models, and ultimately pulling that together with your existing legacy systems. That's how you ideally create this complete digital twin. Here's an example of a flight path for a drone. There's some good discussions from Dexter from EPRI around what you need to do in order to develop flight paths that can give you good quality models of the existing infrastructure. This is photogrammetry. As you notice, photogrammetry is not going to be quite as crisp as the pictures themselves, but this could be a way of kind of organizing those photos. Dexter was talking about the need to be able to know which photos to look at, about the thousands that get taken. If you can navigate a three-dimensional model that's created, a mesh that was created from the photos, and then when you find an area that's of particular interest, say, okay, now show me the high-definition photos that have been taken in this part of the model. That's where I think a lot of these technologies can collaborate. And certainly the AI and ML, I think this has already been raised ahead of time. There is good work being done in identifying and classifying objects when you take these photos, being able to classify these objects and highlight them in the model itself. That's critical if we want to join these models with legacy systems, whether it's SCADA systems or CMS systems. All of the data in those systems are associated with an asset, and so we have to be able to photogrammetry model, identify what an asset is, and then match it with these other systems in order to make everything line up. And then ultimately, the nirvana is not only to recognize those assets, but be able to use AI and ML to track the condition of those assets. So I do want to leave time for questions. I think I'll wrap it up there, but certainly that's our perspective on what a digital twin is, how we think you can start to build a digital twin. And we definitely think that there's lots of opportunities. You need to think big, but start small and scale fast. So Gavin, any questions?
Yeah. Hey, thanks a lot, Brian. I like that the final note there. Think big, start small, scale fast. Well, I'm going to kind of do an amalgam of some questions kind of on that note. And I think actually it could be appropriate to do a little product mention here, because the question about, does this run in MicroStation? So I think people are wondering the nuts and bolts of how it puts together, as am I. Maybe, there's been, products even in the Bentley line that have been doing this for a long time. I remember working in a MicroStation environment in the 1980s and doing connectivity on the vector data of outside plant maps for telephony. So those tools have been around a while. Maybe you could explain the current state of the environment, like the iTwin. Explain what iTwins is and what examples of like where they would go to a different package to do like sandboxing simulations. I wonder if you could go over a few of those.
Sure, sure. Yeah, so I mean, Bentley's legacy is definitely MicroStation and the CAD design tools, and that's still definitely a big area of focus for us. In the latest version of our CAD tools, we've created what we call the connected edition of those CAD tools, and the idea behind that is we've taken these primarily desktop-based design tools that create three-dimensional CAD models, and we've connected them to the internet. We've enabled all of them to publish what we call iModels into our iTwin environment. So Bentley has a cloud-hosted iTwin environment, which is this sort of collaboration platform that we're using for hosting our digital twins. So the idea is, as you're going through design, you are creating three-dimensional models of something that you plan to build. And you can do this, by the way, in Bentley design software or in Autodesk or any of the other major kind of design softwares. Any of those, you can use industry standard bridges and take that information and publish it to our, what we call the iModel Hub, which is hosted in the cloud. And then within that cloud, we can start combining that with these other sources of information. So we can combine it with context capture reality meshes. We can combine it with your CLMS system. We can combine it with your SCADA system. And to us, that is the digital twin. That is where you've taken a three-dimensional CAD model and turned it into a full digital twin that can then be used for some of these use cases.
Okay. Yeah, I got time for just touch on one more. The digital twin models for electric utilities, would this be a mix of point clouds, mesh, and vector data?
Yes, exactly. And these voxels are interesting. I'm interested in finding out more about that and seeing whether it makes sense to overlay those. But definitely we see the digital twin being a representation of a four-dimensional world from multiple different perspectives. So, one perspective is a 3D CAD model. Another perspective is a photogrammetry, a reality mesh that's been created by a whole bunch of photos. Another perspective is a point cloud, a whole bunch of points that have been collected from LiDAR. But our concept is that this platform supports all of these different perspectives on the same assets and then can tie it all together because it understands, this particular piece of this CAD model is the same as this particular piece of this reality mesh, which is the same as this function location in SAP. They're all really the same thing. And so when I click on one, I'm talking about the same thing. So yes, we see those all as different perspectives of the different digital perspectives of the physical object. And to us, that's what a digital twin is.